Good afternoon. This is Wendy Richards with Siewert Equipment. Welcome to the Thickened Aerobic Sludge Digestion Process presentation. Just a few housekeeping items before we begin. During the presentation, in order for you to get your wastewater operator credits and also PE credits, you must complete the poll questions that will happen during the presentation. There will be 5 multiple choice questions to answer by poll vote. You will click on the answer that you think is correct, hit the submit button, we'll post the results, and then we'll move on to the next question. We can actually monitor whether you've responded, so it's very important to get the credits that you do answer the poll questions. And also to receive your credits for this webinar, you must complete the survey evaluation that will show up at the end. So please stay connected until you complete the evaluation. In addition, if you have questions during the presentation, there's a drop-down arrow under the word questions, and we'll do our best to answer them at the end if you type them in. You will also need to download the certificate of completion, which you see there under handouts. There's 2 handouts attached on the dashboard. One is the certificate of completion, and the other is a PDF of this presentation. I'd like to introduce Brian Wu, who is a product manager with Ovivo for the Biosolids Management and Resource Recovery Group. His specialization is aerobic digestion for the last 14 years. And with that, Brian, please take it over.
Thank you, Wendy. I want to first thank everyone for taking the time out of their busy schedule. I know it's been quite a challenging situation lately, but I appreciate everyone taking the time out of their busy schedule to listen to this presentation on thickened aerobic digestion processes. So with thickened aerobic digestion processes, I'm going to discuss how you can learn how to optimize your aerobic digestion systems. A lot of times, when I talk with clients in general, they look at aerobic digestion as just a tank full of diffusers, but we really employ a lot of optimization techniques to really optimize the aerobic digestion process. So with that, hopefully we can, you can learn about some solutions in terms of if you have an aerobic digestion process, you might think about how, we could be optimized. So why is, why should you really care, about managing your biosolids? Why should you care about aerobic digestion? Well, the answers are that, we're only growing as a society. And unless we magically forget how to go to the bathroom, we're only going to generate more wastewater. So to give you an idea here, we have about 15,000 POTWs in the US that treat about 30 billion gallons per day of wastewater. And with that, every MGD, we produce 1 dry ton of solids. So that's a lot of solids that we're producing for our wastewater. So finding ways to manage the biosolids in the most efficient and cost-effective manner is very, very critical. Because if you think about it, sludge treatment accounts for more than 30% of the O&M costs. Generally in the US, I think it's much higher. I think it's around 40 to 50%. And about 45% of the POTWs utilize aerobic digestion. So I think it's important to clarify where it's ideal to use an aerobic digestion process, like what size of plant. So a good guideline from our experience is that aerobic digestion, it's going to be utilized for plants that are 5 MGD or less. Of course, that is dependent. It's highly dependent on energy costs. So if you have high energy costs, and I'm talking about maybe 10 cents a kilowatt hour or more, that 5 MGD might get reduced down to 4 MGD where aerobic makes sense. And say if you have lower energy cost, then that 5 MGD might get stretched out to 8 MGD. So as you can see, most of the solids that are treated in the US, the majority of it is treated with aerobic digestion. So why is it important to really optimize aerobic digestion, and why treat it a little differently than just a tank full of diffusers? Because if it's not managed properly, it could be an expensive one. And some common client concerns related to the management of biosolids, and with aerobic digestion, it's no different. So you have increased solids disposal costs. If you don't stabilize the solids or have a plan to dispose of the solids, you can pay a lot in disposal costs. One of the disadvantages about aerobic digestion are high energy costs in general. So that's one of the disadvantages about aerobic digestion, is that although it is simple, you're going to spend a high amount of money on energy due to the aeration of the tanks. Depending on what type of treatment goals that you have, footprint or capacity can be a concern. And one of the things that, or challenges that I do like about wastewater, is that limits are only going to start to get tighter and tighter. And I don't know if in New York, although you guys are pretty close to the Chesapeake Bay, where you do have some of the issues with the algae growing in the Chesapeake Bay, so you have to control the amount of nutrients that get discharged to the Chesapeake Bay. There are certainly concerns with returning too much nitrogen and phosphorus back to the head of the plant, depending on what biosolids management system you have. Now, aerobic in comparison to anaerobic in general, the nitrogen and phosphorus is going to be relatively low, but depending on how you operate the aerobic system, you can still send a significant amount of nitrogen and phosphorus back to the head of the plant. And typically your main treatment system is not sized to handle that load. It's funny that some homes are kind of near wastewater plants, so obviously controlling odors is a big concern when it comes to managing biosolids. And finding ways and options to dispose of the biosolids is becoming more critical. Landfills are closing down, so there's less options to dispose the solids to the landfill. Landfills are limiting the amount of solids to be disposed of. So finding different ways besides sending it to a landfill is becoming more critical. So Class B stabilization, where you have a land application option, might be a very, very good option for clients to consider. So thickened aerobic digestion, we've really optimized the systems to offer a solution to address all of these concerns. So the first poll question of the day, and I think Wendy.
I will actually be launching it right now so everyone can see it. Approximately how much dry solids does a 2 MGD plant produce per day? And there's 3 choices. Just a reminder, after you've voted, be sure to hit the submit button. Looks like we have about 80% of you have voted. We'll give it a couple more seconds. We're looking for 100% voting so you can get credits. Okay, I'm going to close the poll. I'm going to share the answer. The answer is D, 4,000 pounds. We actually had quite a few people who picked 2,000 pounds, but it was a 2 MGD plant, not a 1 MGD plant. So the answer is D, 4,000.
Thank you, Wendy.
You're welcome.
So thickened aerobic digestion processes. So some of you that are on this call might have heard of pre-thickened aerobic digesters, which was PAD. And now we've renamed them to TAD, Thickened Aerobic Digestion. So these systems integrate thickening with a controlled aerobic digestion system that's ideal to meet Class B stabilization. And these systems, not only do they implement thickening, but they also include process enhancement techniques in order to have a sustainable and successful operation. So these techniques include series and batch operation, thickening, temperature control, aerobic and anoxic operation, and operational flexibility. So all those really are going to be required to have a real sustainable and optimized process. So the thickened aerobic digestion systems that I'm going to discuss are SilC-TAD, which stands for silicon carbide thickened aerobic digester. So we use a silicon carbide membrane to thicken the sludge to be processed in an aerobic digestion process. Next, we have Mem-TAD, mechanical thickened aerobic digestion. So we integrate a mechanical thickener with a controlled aerobic digestion system. This could be like a GBT, a rotary drum thickener, or a dissolved air flotation thickener. And then we have a gravity thickened aerobic digestion system. And we use a gravity thickened aerobic digestion system in a controlled aerobic digestion system. So why would you want to use a TAD system other than, of course, the process optimization techniques that I described? So one is that they feature Class B stabilization in a reduced volume. So if you compare thickening versus not thickening, you're really reducing the volume and the footprint required to meet Class B stabilization. So for instance, if you waste your solids at 1% and you thicken to say 3%, now you're talking about reducing your volume by a factor of 3 to achieve Class B stabilization. Since you have reduced tank sizes, now you reduce your energy as well, because when you size aerobic digestion, particularly for mixing, you're sizing it based on 30 SCFM per 1,000 cubic feet just to mix the tank. So if you reduce the size and the volume of the tank, you also reduce your air requirements. Also, this systems are ideal for retrofits. So if you have some tanks at your plant, or if your plant is up against it capacity-wise, by thickening, you increase the capacity of those tanks. So you may not need any additional infrastructure to meet Class B stabilization. And particularly for a retrofit, if you have longer digestion time, if you have longer capacity in your tanks, you get better digestion and reduced disposal costs. I'm going to present some case studies where we have shown examples of where we've retrofitted thickening into aerobic digestion, how we've shown reduced disposal by increasing the capacity of existing tanks. So the first process is a gravity thickened aerobic digestion process, and it's very simple. A lot of operators know how gravity thickeners work. The most that you can thicken to is 2%, and that's because you're really relying on the settling characteristics of the sludge. So if you have a good settling sludge, the more you're going to be able to thicken with a gravity thickener. But from our experience, the most that you can get thickening wise with a gravity thickener for WAS only is about 2%. So how it works is that you have waste activated sludge go into a premix, then it goes into a gravity thickener where the sludge settles to the bottom, and then you pump the scum and the thickened sludge that's collected at the bottom of the thickener into aerobic digester number 1. So aerobic digester number 1 you basically get a VSR and aeration, and then you loop it back with the premix tank. So you have a continuous looping cycle between the premix tank, the gravity thickener, and aerobic digester number 1. Aerobic digester number 2 does not receive any incoming sludge. It's isolated from the process. So it just basically sits there and aerates. So half the time for the SRT required for Class B is how long you operate digester number 1 in loop. And after the half amount of the time is over, then you basically draw down aerobic digester number 2 and send the sludge to wherever you want to take it. Typically it's dewatering. And then the aerobic digester number 2 becomes the in-loop digester. So it switches functions with aerobic digester number 1 becomes the isolation digester. So that's how the GTAD process works. The next is the mechanical thickened aerobic digestion process. And this is a very, very straightforward process. So you're using polymers to thicken the sludge up to 4%. And this is a really good application if you're looking to convert an anaerobic digester to an aerobic digester, because most anaerobic digesters have some form of mechanical thickened equipment. And then you just basically place it into multiple digesters that can operate in series or parallel. So, again, you get reduced volume, less energy, and you're using conventional equipment that operators know how to operate. So just to give you guys an idea of how the process optimization works when you employ thickening, but also implement some form of a temperature control and have better aeration, let's look at a facility that has an MTAD system. So this is the Lycoming County Water and Sewer Authority in Pennsylvania. So before they implemented the MTAD system, they had a floor-mounted diffuser system, unthickened aerobic digester, and the tanks were uncovered. As you can see, they didn't really get very good VSR. On average, it was 29% over a 3-year period. And the solids in the digesters really weren't thick at all. They were only between 0.5 and 1.5%. So with the MTAD system, we covered the aerobic digesters to improve the VSR in the winter, because in the winter operation, if it gets too cold, the biological activity of the system is severely hindered, particularly when the temperatures get lower than 15 degrees C. So we covered the digesters and we thickened up to 4 to 5% with the GBT. And this gave the plant or the digesters enough capacity to get Class B stabilization. And as you can see, you have very, very good VSR. It's generally between 40 and 70%. And we used our coarse bubble diffuser system. So it really depends on the diffuser system as well. And I'll discuss that in a little bit more detail when we get to that part of the discussion. But you can see that when you increase the capacity as well as improve the temperature, you get better VSR. And with better VSR, you see the differences in the solid reduction. So we fed at 5, we digested out of digester number 1 at 3%, and digester number 2, I think we got maybe an additional 0.5% solids reduction. And you see the differences in the solids reduction compared to the system prior to this. So we were able to reduce the disposal by about 50%. And that gave them an solids reduction of about $37,000 a year. So you see the differences in the solids disposal when you really increase the capacity of the system, as well as provide improved digestion during the winter. So the next one is might be a little bit of a new process for people. It's the SilC-TAD system, and we use a membrane thickener, silicon carbide membrane, for aerobic digestion. And the applications for this are facilities to meet stringent nitrogen and phosphorus limits. So more info on that as we progress later on in the presentations. It's ideal for decentralized facilities with reduced operator staff and Class B applications. So before
Okay.
that, we go, oh, sorry, Wendy.
No, that's okay. I will launch the second question here. Hold on. Which of the following are reasons to use a TAD system? And you've got choices A through E, and be sure to hit submit afterwards. Looks like we've got about 75% have voted. We'll give it another few seconds. A few more votes coming in. Okay, I'm going to close this poll. And I'm going to share the results. 93% of you picked E, and that is the correct answer. It's B, C, and D. Obviously, we're not going to get Class A stabilization. We've been talking primarily about Class B. And with that, Brian, we'll go back.
Thank you, Wendy.
Sure.
So the membranes in a SilC-TAD system are obviously an integral part of the system. And our history with membrane thickening is we previously used a polymeric membrane for thickening. And the polymeric membrane was a very good thickening system for us. But, you know, we did learn some things with operating the polymeric membranes in terms of how we can improve the product and the technology, and the SiC membranes really offer some distinct performance advantages that allow for those improvements that we're looking for. So first of all, the membranes are completely hydrophilic, and why that is because SiC, or silicon carbide, it's a natural material. It comes from the earth, whereas a polymeric membrane, it's a hydrophobic material because it's an oil base and it's going to resist the flow of water. So what I'm getting at is that you're going to be able to filter more water out of the membranes because it has hydrophilic properties. With membrane thickening, probably the most important advantage is that it's extremely durable. SiC is the second hardest material on Earth. There's only one material that's harder than SiC, and for all you ladies that are engaged or married, you might be wearing this material on your finger. And the only material that is harder than SiC, has higher hardness properties than SiC, is a diamond. It's completely resistant against debris or abrasion or damage related to those type of damage. It has pretty high solids tolerance and high chemical and solids tolerance as well. So how does a membrane work? How does sludge get thickened with a membrane? So basically there's a diffuser that provides air scour for the membrane. So one of the purposes of the scouring air, or the diffuser, is to make sure that the surface of the membrane is cleaned. If you have sludge or solids that are completely blocked or completely block the membrane plate, you're basically just taking away the functionality of the membrane. You're not going to be able to really filter any water out of the membrane. So one of the key purposes of the scourer or the diffuser is to clean the membrane. The other is to create a vacuum in between the plates, which allows the water to be filtered out of the membranes. And that's how the sludge ultimately gets thickened. So the solids, or the water that's filtered out of the membrane, it's collected through some series of pipes here. And this pipe is connected to a low suction pump that extracts the water that's filtered out of the membranes. And more on this later is that the water that's filtered out of the membranes, it's high quality, reuse quality water. So the benefits of membrane thickening is you have improved thickening. And by what I mean by improved is when you decant, which is a common operation in aerobic digestion, the most from our experience that you can get is 2%. And it's inconsistent because you're relying on the settling characteristics of the sludge. With this system, you're thickening up to 3% solids, and it's very, very reliable and very consistent. The other is that you don't require any polymers to thicken. So since you don't have any polymers, you have less O&M associated to thickening. So with really any of the TAD systems, the SilC-TAD is no different. You basically have reduced footprint of the membranes because you're thickening the sludge. So you get Class B stabilization and reduced volume, reduced tank sizes, ideal for retrofits. And because there are less reduced tank sizes, you have less air requirements and energy usage. And probably the most unique advantage of the membrane thickening system is it produces a high quality permeate. And the permeate is the water that's filtered out of the membranes. And that clear glass of drinking water is the type of quality of water that you expect to be filtered out of the membranes. So when we talk about why this system is ideal for B&R applications, the reason is because this water contains very low amounts of nitrogen and phosphorus. And because it's reuse quality and because it has very low amounts of nitrogen and phosphorus, it gives you some options and some operational flexibility. So first is that certainly you can take it to the front of the plant for sure, but you can also combine it with your effluent, because we learned in engineering school the key to pollution, the solution to pollution is dilution. And you also can consider sending this to disinfection as well. And keep in mind that the treatment and the very low nitrogen and phosphorus in the permeate, it's all managed biologically. There's no chemical addition required. It's also a economical solution if you're evaluating it over the life of a wastewater treatment plant. So let's take the Fruitland wastewater treatment plant as an example. So some background on the Fruitland wastewater treatment plant is that it was a 0.8 MGD SBR. They were upgrading the SBR to do ENR, enhanced nutrient removal. And they had 2 conventional aerobic digesters. And these digesters did not provide enough capacity for Class B stabilization. So the consulting engineer for this facility had to consider some thickening alternatives to optimize and make best use of the existing infrastructure. So they were considering gravity thickening, mechanical thickening, and membrane thickening aerobic digestion. So what I find very interesting about this evaluation is not that the membrane thickening process had the highest capital costs, but really how even it is. It's not much more expensive than mechanical or gravity thickened aerobic digestion. So why is that? The reason why is because the mechanical thickener required a building, and buildings can be very expensive to house a mechanical thickener. With gravity thickening, because you're only able to thicken to 2%, they had to build an additional digester to achieve Class B, whereas membrane thickening required the least amount of infrastructure, just an anoxic basin and a membrane thickening basin. Now, where the membrane thickening system really shines is on the operating costs, as you can see. Remember, no polymers required for thickening, no chemicals required for nitrogen and phosphorus management of the side stream. With mechanical thickener, you have the polymers, and then you have the time it takes to man mechanical equipment. With a gravity thickened system, there's not much O&M per se, But the fact that it required an additional digester, it had the highest energy cost of the three alternatives because of that additional digester. So you have the additional energy cost for aerating that additional tank. So when evaluated over a 15-year life, the membrane thickened system actually was the cheapest alternative of the three. So the SilC-TAD process, this is what it looks like. And how it works is basically we have a screen that screens the waste activated sludge. And the reason why we screen is because, and we screen it with 1 millimeter with a bar screen and 2 millimeters with a perforated plate screen. And the reason why we screen it is to protect the integrity of the membranes. So the wasp goes into an anoxic basin. It's mixed with a submersible mixer. Then it goes into a membrane thickening basin where the permeate goes to wherever you want to take it. And then the thickened solids get left into the membrane thickening basin. It overflows into the in-loop digester where you get the majority of all the solids reduction, but also the nitrification to occur. And then it overflows back to the anoxic basin. So you get a continuous looping cycle between an anoxic basin, the membrane thickening basin, and the in-loop digester. So this looping cycle is the key to why we're able to have very low nitrogen and phosphorus in the water that's filtered out of the membranes. First, you have nitrified sludge going into the anoxic basin, so you get full night D-night, and then you got your carbon source coming from your WAS, so you get the denitrification, so that's how we're able to get total nitrogen removal. And the phosphorus, how we manage the phosphorus is the membrane thickening basin, it's continuously aerated. So we don't allow PAO bacteria to release phosphorus into solution. It basically stays in the solids. So with the in-loop digester, the other thing that happens is that also a small portion of the sludge goes to the isolation digester where you get the majority of the pathogen removal to get to class B stabilization. So if you will, this really is kind of like a BNR facility, but a BNR system and a solids handling process. So poll question number 3, Wendy.
Okay, I'm on it. Let's see. Question. Which of the following are reasons to use a SilC-TAD process? That's that silicon carbide. Please select one. I do want to note that if you're having trouble voting, try reducing the size of your screen. Or if you really can't do that, you can send answers to Sherry after the presentation or now. I think number A, thickening in this process does not require polymers. The N is missing from not.
Yeah, so
Okay.
I fall into a bad stereotypical engineer, Wendy, where I'm not very good at spelling or grammar. I'm only know numbers.
And actually, the answers to this are a little confusing because there were some changes made at the last minute. So rather than number E saying choices B and D, I want to point out that number E says choices A and C. Sorry for that change. We see about 85% of you have voted. I'm about to close the voting. If you need any clarification, let us know. And I've closed the voting. Okay, so the answers are A and C. And sorry for the confusion. It looks like the majority of you did pick those two, and E was supposed to read A and C. And with that, we'll move on to the next.
Yeah, I must have, well, I can't say that I have silky bed sheets, but maybe that's why initially I made the error. I don't know.
It looks like Brian got it right, so.
So with thickened aerobic digestion, obviously I discussed about a lot of the great advantages to thickening. However, there could be challenges if, thickening is not, if all the challenges with thickening are not considered. And one of the key challenges is that you have to have the right aeration system for a thickened aerobic digestion process. You cannot just put in a fine bubble diffuser, because if you do, you can have quite a few challenges, if you don't have the correct aeration system. Some of the challenges could be you could, clog the diffusers. You won't get good mixing in your digester. You'll have a lack of oxygen transfer efficiency. And if you don't get the right OTE, the performance of your process may be hindered. So obviously you need to have the right aeration equipment with an aerobic digestion system. So we have a lot of experience with thickened aerobic digestion, and I think a lot of it has to do with the fact that we have the perfect diffuser for a thickened aerobic digestion application. And the type of diffuser that we have is the single drop diffuser. And how it works is if you had like a cup of water and you put a straw in that cup of water and raise it about 1 millimeter off the bottom of the cup and blew air into it, that's basically how the diffuser works. So one of the key advantages of this diffuser is that the orifice is completely accessible. It's not submerged in the liquid level, and the orifice is the only part of the diffuser that requires access in order to maintenance it. The diffuser alone is mainly a non-clog diffuser, but in the rare event that the diffuser does clog, all you have to do is just unscrew that orifice cap that you see here in the picture on the right. You stick a rod or a pressure hose down the drop pipe and get the clog out. It's like cleaning a gun for some of you gun enthusiasts out there. One of the advantages to this too is because you're able to access the orifice, you don't have to drain the tanks or take the tanks out of service. So if you have, say, a floor mounted diffuser system and it clogs, the operator has to go into the tank, drain the tank, and clean the diffusers. Obviously, it's not a fun chore, and this design completely eliminates that having to do that. So the single drop diffuser alone can aerate solids up to 3%, but if you wanted to mix very thick solids, you would add either a shear tube or a draft tube to the single drop diffuser. And how that works is that they basically both function as an airlift pump. So you're basically pumping sludge from the bottom of the basin up to the top of the tube, and you basically get this airlift pumping action, and this increases the velocity of the mixing, and that's how you're able to mix very high solids. The shear tube, it's a single tube that goes around one single drop or each single drop diffuser, whereas a draft tube, it's a bigger diffuser with multiple diffusers inside of it. Also, one of the advantages of this is that the diffuser discharge point is actually halfway into the tube. So it's not submerged all the way down to the bottom of the floor. And that reduces the discharge pressure requirement for your blower system. And this is what the aeration of the system looks like. So the center portion of the tank is being mixed with a multi-adductor draft tube, and the outside of the tank is being mixed with the shear tube aeration. So as you can see, you got very, very powerful mixing with this diffuser system. And then we also have an option where we integrate a flat panel aluminum cover. As we know, temperature control, particularly when it's cold, and it does really get cold in I guess most of the part where most people in this audience is from, which is the East Coast, and the cover really optimizes the VSR in the winter time. So not only do you have issues with lack of VSR if the temperature gets too cold, but you also have ammonia accumulation that can occur because nitrifying bacteria activity is severely hindered when the temperature is below 15 degrees C. And this cover system really provides a good solution to manage the temperature when it gets too cold. So the cover system, we call it an air beam cover, uses the beams, the support beams, as air channels to provide air to the single drop diffuser system. So we integrate all the diffuser systems that I just showed you, whether it be the single drop, the drap tube, or the shear tubes with this cover system. And the black dots that you see protruding above the cover are the orifice. So you can physically stand on this cover and have access to the orifice system. So obviously this, has very good temperature control, and it should provide some good odor control as well. Wendy, next poll question.
Yep. Let's see. Hold on. Okay, question number 4. I will launch. Which of the following are correct about a single drop diffuser system? Please select one. Looks like we have some pretty quick voting by the majority of you. Must be an easy question. We'll give it a few more seconds. Okay, it looks like the majority of you have voted, and the right answer is, sorry, I'll share that. E, choices A, B, and D, and 91% of you got that right, so good job.
So now we move into case studies where we've collected data from several of facilities that operate the diffuser system along with the TAD process. So they say the proof is in the pudding, and I find it ironic I talk about sludge and it looks a little bit like pudding. So the first one I want to talk about is Frackville, Pennsylvania. And with Frackville, they had aerobic digesters that were not covered, and their belt press was pretty close to capacity. So the engineer, well, not the engineer, but the operators felt that the solution was to increase the size of the belt press to handle their solids or manage or dewater their solids. But the engineer had an idea with their experience with Ovivo's aerobic digestion systems. The belt press was a good piece of equipment still. It was in good shape. Maybe there was another way to optimize their solids process besides increasing the size of their belt press or getting a new belt press. One of the ideas they had is, okay, you have these open top covers, you stabilize the sludge by adding lime. So maybe we can get rid of not having to add the lime and provide improved digestion and send less solids to the press. And by sending less solids to the press to process, maybe that would prevent the plant from not having to buy another belt press. So that's the direction that the engineer went with, was they invested the money on improving the digestion instead of buying a new belt press. And some history on this is that, again, their aerobic digesters were not covered. They had floor-mounted coarse bubble diffusers. They added lime to stabilize because they weren't getting the VSR required to meet Class B. And they were also adding ferric to control the phosphorus. Now, we didn't, implement any type of thickening. What we did is that we added the air beam covers to improve the temperature and hence improve the volatile solids reduction. And that's basically what we did here. So we have the cover and the single drop diffusers with shear tubes to improve the temperature in the VSR. And this is what you see here. This is what the covers look like at Frackville. And then you see the SBR tanks. And then this is what we meant by the goal of the system to reduce the solids being sent to the belt press. You can see before the air beam system and comparing it after the air beam system was implemented, the amount of solids that were reduced as a result of improving the digestion by just simply covering the tank and providing a better diffuser system. They realized some savings, a 57% reduction in solids. That was only about a $17,000 annual savings. They were able to get an energy rebate from the Pennsylvania Power and Light, which is their energy provider, and they showed a substantial amount of energy savings as a result of using our system. Remember, the shear tube system, the diffusers are not submerged to the bottom of the floor, and that reduced the operating horsepower on their blowers. Other benefits were that they didn't need any lime for land application. We were able to get a Class B stabilized product. And because of the improved digestion and implementing aerobic and anaerobic cycling, they were able to minimize the amount of P going back to the head of the plant. So they eliminated adding ferric for P removal. So now we'll go into the membrane thickening, and the first one I want to talk about is Dundee, Michigan, which was the very first US installation. And some history on this is that the way that they dispose of their solids at this facility is they land apply it. And the way they land apply it is they subsurface inject it. And if you have, I guess, too much snow on the ground, it could be very challenging to subsurface inject the solids, onto the ground. So they basically had to limit their solids disposal to 2 times per year, once before the snow hit and once after the snow hits. And what happened before is they had a conventional aerobic digester. They only thickened to 2%, and they only got 120 days of SRT. They needed 180 days of SRT, again, to limit the times that they disposed the solids. And all Ovivo did was just add in the membrane thickening basin, thickened to 3%, and they were able to get the required holding time so that they only dispose the solids twice per year. And I mentioned one of the advantages of the membrane thickening system is that you get very good water quality that's filtered out of the membranes. And you can see here that you basically have non-detects on both the ammonia and nitrates, and the phosphorus is just a little over 1. And that was 1.5 years worth of data. The next one that I want to talk about is McFarland Creek, and this is a 2-stage membrane thickening system. So what's unique about this is that we put the membranes directly inside of the digesters and we thicken it to 2 stages. So the first one we thicken to about 2%, and that's to optimize the flux rate and reduce the capital costs of the equipment. And then in digester number 2, we thicken it to about 4%, where we used a more derated flux rate. And again, this was a retrofit. And what I wanted to show here is that, again, by increasing the capacity of the tanks through thickening, improving the digestion, what kind of impacts that it has on your dewatering system. So without the membrane thickening, they were operating the belt press about 57% more than when they implemented membrane thickening. And then and that is because they sent substantially less solids to the press to process. And you see the reduction in the amount of solids that were produced by the plant as a result of improved digestion. You got 41% reduction of solids disposed, and then you had reductions in polymer because there was less solids to dewater. And you can see all these had cost savings in terms of solids disposal and polymer cost. And then maybe closer to home, there we have a membrane thickening system. It doesn't focus on stabilization, but it focuses on thickening. So at Woodside, they transport the sludge in liquid form to another facility to be processed. And they actually pay a pretty penny to do that. I think they pay about 10 cents a gallon to haul their solids to another facility to process. And by thickening it to 3%, we were able to reduce the number of hauling trips, the number of trucks, because basically you're removing the amount of water and you're disposing more solids. And as a result of that, you see substantial savings and a very, very quick payback. So next poll question, Wendy.
Okay, this is our last poll question. Hold on a second. Number 5, which of the following was not a benefit from having an improved digestion process at the Frackville, Pennsylvania facility? Please select one. This looks like another easy question. We see a lot of responses. Good to see you're paying attention. Couple more seconds. All right, I think the majority of you have voted, and I'll close that, share you with the answer. Obviously, the answer was B, operators got free beers from a local bar. That is what was not a benefit, although we don't know if that was the case. So with that, Brian.
Of course, Wendy, they might have celebrated with some of the benefits that we provided them, right?
Yeah.
Okay, with that, that's the conclusion to my presentation. And what I want to kind of leave you guys with is that when you optimize your aerobic digestion system, not only do you have the benefits on the biosolids management portion of it, but it also improves other parts of the plant, like dewatering, as you saw from the case studies, but also the main treatment process. Because if you send too much nitrogen and phosphorus back to the head of the plant, like Frackville, you could end up, adding, chemicals to manage that additional loading. And that's loading that the main treatment system is not designed for. So really, again, if you take, a lot of optimization into your aerobic digestion into account, not only is it going to help you manage your biosolids, but also, again, help you to manage your overall wastewater operations. And with that, I'll go ahead and entertain any questions. And I believe the questions, Wendy, correct me if I'm wrong, are on the chat, correct?
Yes, under questions.
So
I want to thank you, Brian. So if you do have questions, feel free to type them into the questions box. I do think it's pretty impressive, some of the cost savings for optimizing aerobic digestion that can be achieved. Obviously, aerobic digestion is pretty common in upstate New York. for plants that are less than, say, 5 MGD, maybe even 8 MGD, depending on energy costs.
To add to that, Wendy, besides energy costs, and energy costs being the main factor, another factor that can come into play is the type of wastewater it receives. So in other words, Wendy, if it receives a high amount of industrial load or a wastewater that's very high in BOD, that would be another reason as to why to go with an anaerobic versus an aerobic digestion process. So if you have a lot of biodegradable organics in your wastewater, even though the flow of the plant might be small, it might make more sense to go with an anaerobic digestion process.
Right. So I do see one question, Brian. What is the membrane pore size?
The membrane pore size is 0.4 micron, and that's an ultrafiltration membrane.
Okay. I see. I have a little trouble reading the questions. I don't know if Sherry can see them. What percent?
Yeah.
150,000 POTWs in US. Any idea what percentage have aerobic digestion?
Well, I think it was 15,000, and the percentage, I believe, approximately is 45%. Now, there's more plants that have aerobic digestion, but in terms of treating the overall, billion gallon, I think it was like 30 billion gallons of flow, anaerobic digestion is going to treat a higher volume of solids compared to aerobic, but there's more quantity or more aerobic plants, and the estimate is around 45%.
Okay, another question. Where are you getting the 1 dry ton per million gallon treated? This person writes, I receive sludge from 2 plants and they are both 0.75 MGD and they both produce about, 60 tons per year. Dry tons.
Well, I think Wendy, that's obviously way off from my estimates, but I think I don't recall the source that I got it from. That's just a general guideline for municipal wastewater plant. I don't know, like, per se, if that 0.75 MGD, Wendy, is from maybe receives quite a bit of industrial load, where it's going to be prone to generating a high amount of solids. But for a municipal plant, I think that's a pretty good rule of thumb, is 1 MGD will produce about a ton of dry solids.
Okay.
I think that might have come from Metcalf and Eddy, but I'll have to get where we got that information from.
Right. I'm going to ask one more question, but before I do, I want to remind you there's 2 handouts that are attached. One is your certificate of completion you should download before you close out. The other is a PDF of the presentation. They're both here on handouts. And then also, in order to receive your PE credit or operator credit for this, you must complete the survey evaluation that will show up at the end. So please stay connected and complete that online. And with that, I'll ask one more question of Brian, and then I'll let you get to that survey. Regarding the question concerning the single drop diffuser, can anything really be touted as lasting the entire life of a wastewater plant?
Well, we have lots of installations with the single drop diffuser. It's 1,000+ plants, and the majority of them last at least 20 years. And we would define the life of a wastewater plant as 20 years, and we really haven't had to really replace any parts or equipment in 20 years, and we've actually had some plants last 30 to 40 years. So from our experience, that single drop diffuser is a very, very robust system.
Right. Okay, thank you. So there will be a recording of the webinar as well, and I think when Sherry sends out the information to the participants. There will be a link to a recording.
Yeah.
And with that, oh, go ahead, Sherry.
Yeah, there will be a link to the recording. And if you don't get the, I'm sorry, I'm getting feedback here. And if you don't get the PDF handout, it'll be attached to your follow-up email tomorrow too.
Okay. Well, thank everyone for coming. I hope you learned something, and feel free to reach out with questions to myself, Wendy Richards at Siewert, W. Richards at SiewertEquipment.com. Thank you, Brian.
You're welcome, and I want to thank everyone for their time attending today, and I hope that you found some parts of the presentation at least insightful, and as Wendy mentioned, hope you learned something. So I want to express my gratitude for all those that attended.